All right, recording is rolling. So, all right, it is Friday, January 13th. We're gonna do this list of stuff right here. Let's start with Sydney survey. Show you guys what's going on with this. So, if you guys know Sydney Ashford, she's doing a research survey for a AP capstone. If you could help her out, take the survey. I did post the link to Google Classroom. There it is right there. I haven't taken it myself yet. I haven't read the questions, but supposedly it's only like 5-10 minutes. So if you could, that would help her out. Be awesome. Whoops. No, stop that. Okay. Sorry. And if whoops, if you're watching the video at home, then there you go. I think. All right. It's back over here. All right, let's do ripple tank. Ripple tank. Hey. Okay. Yeah.
You have tape I can use.
Here.
Okay. Thank you so much.
Yeah. All right. So. All right, so I got a plate of water here. You guys see this little nozzle right here? When I hit this on switch, it's gonna vibrate. Zzz. Can't quite see it, but what if I take this plastic arm, right? I pop this in right here. It just touches the top of the water. It brings it back here. Ooh, look at that. Right, you guys see some ripples going out? I got a knob on this. I can change the frequency. Can you guys hear the buzzing? Okay, no, listen real close. You hear a pitch shift. See, as the pitch goes down, as it goes up. Okay, so do you guys see an inverse relationship between the pitch and the wavelength? Right, like the lower the pitch, the longer the waves, the longer the wavelength, and the higher pitch, the shorter the wavelength. Okay, well, you guys see the dark parts. It's probably like crest to crest. You can imagine, right? Yeah.
What is that?
The ripple tank. Wait.
He just walked in.
Okay. So what's going on here is I got a plate of water. I got an arm attached to an oscillator. It's going bzzz, right? Yeah, so it's in out ripples. Okay. Now, do you guys remember waves? What's the connection between wave speed, wavelength, and frequency? So speed equals wavelength times frequency, right? You guys know that? All right. So now the speed of the ripples through the water is just whatever it is. The speed is just whatever it is, right? But okay, so as you increase the frequency, that's going to decrease the wavelength. So there's an inverse relationship then between the frequency and the wavelength. Right. We put different stuff in here. Right, a couple things here. See some reflection. See some wave reflection going on. Okay. Actually, a more exciting type one. I think it's more pretty good. Let's go convex. A little bit of interference going on, which is concave. And switch out the nozzle too. So got this double nozzle. It's like an interference pattern type. It's like one of the new posters. This interference. And how about if I bring in this guy right here? Ooh, what do you think that's going to do? Ooh, like a straight wave. I don't know what's like been on the left side. It's kind of weird. Oh, it's happened.
It's not connected.
There we go. And that's right. All right, so that's pretty fun. Actually, let's take this whole thing and set it over here. Ooh. All right, you guys ready for our lights? Lights. All right, so let's take rest, and we've got a short period today, so take the last 20 minutes here and do some more textbook problems. Okay, and then next week I got lined up for you guys a speed of sound lab, and let's do an in-class quiz on Thursday. Right, so all right, your guys is right, and we'll do that then. Alright, so the last one we did yesterday was number 83 with the earthquakes. You guys remember the whole like system of equations? Take a few pieces of paper and hold it. All right. There was one thing that threw me too, and I realized going on and check this after the fact. They have the primary longitudinal waves traveling slower than the secondary shear waves. So I did Google and fact check that. That's usually not the case. So I think they got their speeds backwards, and then I kind of messed up my math too while I was trying to solve that. So anyway, the recording on Google Classroom is actually from a later class period, so I went a little better, a little bit neater job on that then. Okay. All right. Number 87. Sketch the result for 4 cases shown, in which the centers of the 2 wave pulses line up and they overlap. Okay. So some of you guys is new. Where? Oh, here. Let me break out the relevant poster. Gotta dig through and find this thing. There's no, that's not it. Okay, here it is. Here it is. So one of you guys' new posters involves this constructive and destructive interference. You guys know that? Okay. Now I'm just showing it pretty simple, just like adding amplitudes, subtracting amplitudes, but you could do that at like every single point along that pulse, right? You know what? Let's yeah. All right. It's number 87. So these 2 pulses are headed toward each other, right? And we want the centers to overlap. Okay? So there's really 4 questions going on here with this one. Okay. Okay. So first question: what happens when you overlap this pulse with another pulse that's the exact same shape? Right. So these 2 are going to line up center to center. Right. So I'm taking that and that, and they're overlapping. Right. So I just drew them right on top of each other. Okay. Do you guys think that 0 plus 0 is going to be 0 here? You know, I'm going to change pink color. How about that? Let's do the answer in pink ink. Right. So the 2 individual pulses are in blue, and the answer is going to be in pink. Right. Right. So 0 plus 0 is 0. That's just going to 0 out. Yeah, no big deal. Right. Same thing on this side. All right. What about all this pulse stuff? Right. So it's going to be a point here. Right. Do you guys think that this max point, since they're the same, like 1 unit and 1 unit can make 2 units, it's going to be like way up here, you guys think? Right. And if they're each linear in between, do you think that the resultant is also going to be linear? Right. So like if this is half a unit, that would make 1 unit. Yeah. So this whole thing's going to be like a straight line right here. Okay. So yeah, there's that 87 part. Well, they said part 1. Maybe I'll call it A, like part A. Right. Get that. Like way up. All right, how about question B? All right, so question B looks like this. So I'm gonna take these 2 pulses, line them up, And we'll see what from there. So one's going like this. And the other wave pulse is doing something kind of like this. Okay. All right, that's where they're aligned center to center. Okay. All right, so let's do the answer and so what's that gonna look like? Well, all those zero stuff is just gonna zero out for sure. Okay, so yeah, done with that. Okay. This looks like 0 plus 1, right? You guys see 0 plus 1? 0 plus 1 could be 1, right? So that's gonna constructively interfere here. Okay. This could be like half a unit plus half a unit. Is that gonna be like right there? Half plus half is 1. Right? And what about this far end? That's 0 plus 1 is 1. Okay. What's 1/4 plus 3/4? 1. Right? So like any point you, any like location you pick in between, it's always gonna add up to what? Yeah, like same amplitude, right? Like that. So that's gonna be like a rectangle looking pulse. Well, just at the one instant they're crossing. Okay, and you guys saw the videos of these play out too, which said the pulses are just gonna go ahead and cross through each other. But like if you got a photograph of like one frame, like right at the moment they were lined up, center to center, that's what it looked like. Okay. Okay, guys, good. All right, question C. See what we got. Ooh, they flipped one of these guys upside down. Ooh, all right. Try that. So there's one pulse all by itself. That's right. Okay. The other pulse coming in from the right, moving to the left, is doing like this. So there's each individual pulse, right, when they're going to line up center to center, right? For the rest of the string, I'll just go ahead and zero out here, so whatever. Okay. All right, now the part where the pulses themselves are overlapping. Right. So what's 0 plus -1? Could just be -1. So there's definitely a point right here, right? Okay. How about right in the center? What's +1/2 and -1/2? It's going to zero out exactly, right? And what's the 0 plus 1? Could be 1, right? You guys see what it's going to look like, right? Right. So a couple more. Okay. What's +1/4 plus -3/4? Yeah. -1/2, right? Right there. And what's +3/4 plus -1/4? +1/2, right? Okay. So you guys see the pulse is going to do this thing, zoom, like that. You guys can line those up and do that. Okay, and last one, part D. Okay, so one upright, one upside down. So line up like that, center to center. All right, but some of you guys see the answer already. Because they're just gonna cancel out, right? You guys see that? It's gonna, right, they're just the exact opposite of each other. Okay. So right at the moment they're across each other, they're gonna exactly flatten out. Okay. Actually, the constructive or the destructive interference demo that I showed you guys the other day was kind of an example of that, right? Because there was one snapshot where the rope was exactly flat. Right? You guys know that too, right? But then of course the pulses just went ahead and crossed through each other. All right, guys with us? And then yeah, this could be the basis of anything that involves waves, a lot of the computer files, sound files, music files, right? How do things like add together, mix, harmonize? Right? Foundation right there. Okay. Constructive and destructive interference. What is the period of a pendulum with a length of 1.4 meters? It's number 88. Well,
We don't know where it
let's
is.
let's make a reasonable assumption. How about that?
Wow.
Right. So so all I explicitly told you was the length is 1.4 meters, right? which is a little bit less than 1/2 meter sticks, right? A little bit less than 1.5 meter sticks, right? So pretty long, right? What's a good reasonable assumption you could make so that you could answer this question? Gravity field could be about 9.8 or 10 meters per second squared. Like, pick your favorite. All right, so we could give you guys a head start. See if you guys can solve that. You guys see all these posters hanging from the ceiling that matches your notes. One of those could help you out, or if you remember from your lab beginning of this week, help you out too. What do you guys get? All right, how about now? Who's got now? Yeah, let's go.
0.88.
Ooh, I think I got something longer than that. Wait, that's for time period, right? Yeah, the time period. Okay, so what'd you get?
2.35.
You got 2.35. Okay, all right. So somebody got getting 2.25. Sounds about right. So you guys did time period is 2 pi times the square root of L over G. Okay, it's the answer to you guys' lab from a few days back. And then just pop in the parts. Okay, about 1.4 meters and about 10 meters per second squared. Okay, yeah, I think it's like 2.35 seconds, sounds about right. Let's actually try this out. Got a really long string here. And you get 1.5 meters about. Pretty close, 1.5 meters right there. Click a bob to it. How about this guy giving a bob? Okay, let's put this right here. Okay, the string's about 1.5 meters long. String has negligible mass compared to this bob, right? Okay. So gotta hold it right about here. It's about 1.5 meters long. Okay, so it should be between 2 and 2.5 seconds. We'll be back and forth. Let's look at here. That'd be about 2 to 2.5 seconds. From there. Pretty close, right? All right. Pretty close. Well, that finishes chapter 14. You guys got any questions on chapter 14? Good there. All right, chapter 15. All right, 52 down here in the corner. You hear sound of firing of a distant cannon 5 seconds after seeing the flash. How far away is the cannon? 5 seconds. I guess a reasonable assumption here is that light travels so fast. Like the speed of light is like 3 times 10 to the 8 meters per second, which is so crazy fast. You can basically assume this is instantaneous. It's like many orders of magnitude faster than the speed of sound. In fact, speed of sound. Yeah, speaking of which, that might be helpful to know for something like this. Is that a number that we've been using this week? No. So maybe other classes have been coming up. Does anybody know speed of sound in the air? About? Yeah, I think you're right in terms of miles per hour. Yeah. Let's use about 340 meters per second or so. Right. Now that depends on the temperature and the pressure, but kind of a nice middle number to use. Okay, so sometimes you see a little like 331, or sometimes you see 343, depending on your assumption. Okay. Yeah. All right. So we got that speed. We got a time interval of 5 seconds. Okay. Can you guys get how far away? All right, who figured it out? So 1,700 meters, you guys are saying? Yeah, because this goes way back to, it was one of the first things we ever did, right? Distance equals speed times time. Okay, so you got 340 about meters per second. Multiply that by 5 seconds, seconds canceled. Yeah, 1,700 about meters. Okay, how many kilometers is that? Yeah, 1.7. Does anybody know pretty close to how many miles that is? Yeah, it's about a mile. Yeah. The conversion from kilometers to miles or miles to kilometers, it's really, really close, like just randomly really close to the golden ratio, which is like 1.62. So it's about that 1.61 more 1.62, somewhere in there. Right. And this is really close to that ratio. So you guys ever hear think about like seeing a lightning flash and hearing the thunder and counting the seconds? What are you guys told for like how many seconds supposed to count? How does it work? Yeah, 5 seconds is a mile. Yeah, and that's exactly what we just confirmed, isn't it? Right? Yeah. So you see a flash, right? You count the seconds. Suppose you count 5 seconds here, hear the thunder. That means that lightning strike was a mile away, right? What if you count off 15 seconds and then you hear the thunder? 15 seconds. How far away? Yeah, 3 miles, right? So number of seconds divided by 5 tells you the number of miles. Okay. The rules for kilometers is you instead divide by 3. Right. So here's like the fast way to do it in terms of kilometers. Say, well, I heard 5 seconds. Go ahead and divide by 3. That should tell me the number of kilometers approximately. Yeah, 1.67 kilometers. Oh, look at that. That's what we've got. 1.7 kilometers. Right. So hear lightning strike. There's a see lightning strike. Hear the thunder. Divide by 5 to get the number of miles. Divide by 3 to get the number of kilometers away. Okay. And then ratio of 1 mile to 1 kilometer is actually really close to the 5-to-3 ratio. 53. You shout across the canyon and hear an echo 3 seconds later. How wide is the canyon? All right. Anybody solve for how wide is the canyon? What do you get?
514 meters.
Is that Helen?
514 meters.
Here, let's solve it. See. Okay. So, okay. So you count something. Got the sound waves. Right, go across the canyon, and then they have to reflect and go back. Right, that's what an echo is. Right, it's like a sound reflection. It bounces off the boing. So whatever this distance is.
510 meters.
Okay. Yeah, actually, I think you guys are right. Yeah. Or yeah. Right. So check. Wherever the distance is x, right? It really has to do a double that distance. Yes, it sounds right. So, but you guys are saying about 500 some meters. Okay. Actually, that doesn't sound right. Okay. So it has to travel twice that distance. Right. Say at the speed of sound for some time. Okay. So we're trying to figure out what is that gap. We're doing about 340 so meters per second. And that was 3 seconds. Or an alternate way to think about it is that it's a second and a half across and a second and a half back. Okay. All right, so 340 times 3 divided by 2. Yeah, there you go. All right. You guys got it? Some meters. All right, let's go back. 68. A fire truck is moving 35 meters per second. The car in front of the truck is moving the same direction at 15 meters per second, so going slower. So there's a vehicle in front of it going slower. And then this fire truck is blasting a 327 hertz siren. What frequency is heard by the driver of the car? Ooh. Yeah, you're right. You're right. It would be more than 347 hertz. That's a good thing to notice because that'll help you frame this problem. Where's the slide I'm looking for? If you guys know how to solve it, go ahead. I'm just digging through my notes and trying to find a particular poster here. Here, all right, here's the poster I'm looking for. Which poster I'm about to flash up here? One that says what? Boom, Doppler effect. You got it, right? So something to do with this, right? Okay, now the observer, I just drew as a stick figure, but we could just replace this with another vehicle that's just going really slow, right? Here's the fire truck. Right? So it's going like this, right? Fire truck's catching up to the car. Right? But they're both like traveling to the right on this picture, right? And then what's the observed frequency of that siren? Okay. So you guys see what's going to feed into what, right? Like the source frequency, like if the fire truck was parked, that's the number they gave us. That's the 327 hertz, right? And then, okay, we got the speed of sound here and here. We're going to plug in a reasonable number for that. We've been using 340 meters per second today, so keep it at that. Yeah. And then we got the observer and the source speeds. Okay. So one of this could be the vehicle you're listening in. The other is the fire truck. Right? Fire truck is like the source of the sound. All right, and now here's where the logic has to kick in. Is like, how do you apply these plus or minus signs? Okay, so let me get this down on paper. You guys can navigate this. So the observed frequency is the source frequency, that many hertz, multiplied by speed of sound, and speed of sound is there and there. Notice if everybody was parked, nobody's moving, it'd be plus 0, and this ratio would just be what? 1, okay? Which means the frequency wouldn't change. The observed frequency would match the source frequency. Okay? But we're going to have the car going at 15 meters per second. So that's like the observer, the car 15 meters per second. And the fire truck's going at 35 meters per second. Wait. You should know this. All right. In American units, that's 78 miles an hour. Right. All right. But what I want you guys to figure out, right, is what should the signs of these be? Like plus or minus here and plus or minus here. Now, the fact that the car is like trying to drive away from the fire truck. Let's treat that in isolation first. The car's trying to drive away. Would that by itself cause the frequency to appear to go up or down? Right, so let's say you're staying out by the sidewalk and here comes the fire truck. Right, just single note, right? So if it's headed towards you, that's gonna be a high pitch. And when it's going away from you, that's like a low pitch, right? So, and then like you running away from the fire truck could be the same thing, right? Going away would like extend the sound wave, right? It's like this red bit, right? Like two objects moving away from each other is going to stretch it out, right? Which is going to decrease the frequency, right? Remember, speed equals wavelength times frequency, and the speed is the speed of the sound wave is just whatever it is. Once the sound is going through the air, it's going at whatever speed it is through the air. In this case, 340 meters per second. That didn't change, okay? But wavelength and frequency have an inverse relationship. So the longer the wavelength, the lower the frequency. Right? Okay. So the fact that the car in isolation would be moving, trying to move away from the fire truck, that would cause an effect for the frequency to decrease. Right? Just by itself. Right. So what sign would you have to have in the numerator to make that true? Yeah, it has to be minus. Right, minus. So we're going to subtract on top. Right. Now let's switch over and think about what the fire truck is doing, because the source speed is this number here. So we're going to do that. The fact that the fire truck is moving towards the car, right? Now, actually, the fire truck is moving faster than the car is moving. So this is going to be like the dominant effect, right? Time out here. What if they were moving the same speed? What is like 15, 15? When the numerator and denominator match again, and so this ratio would just be 1 again. Right. Okay, so you get that. So this fire truck is headed towards the car. That's gonna be like this blue wave effect, right? It's gonna like shorten the wavelength and increase the frequency. So how do you therefore increase the frequency? Should you add or subtract from the denominator? Also subtract. Because think about what that is, that decreases the denominator. When you divide by smaller numbers, which is what's going on, that's gonna blow up your fraction bigger, 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 which would show an increased frequency. Right, you guys get that? Oh, here, I'll give you guys an alternate perspective. See how it's minus and minus, right? So some other teachers might emphasize the fact that that's also an indication that both vehicles are traveling the same direction, right? If you see the same sign in the Doppler equation, top and bottom, that means that both the observer and the source are moving in the same direction. Right, so let's do 327 multiplied by 340 minus 15, all divided by 340 minus 35. Okay. And you guys are right to say that the observed frequency overall is going to be more than the source frequency. You guys get like 348 about hertz. 348 hertz. All right. So that is a perfect pause point. All right, bells about to ring. You guys have a great 3-day weekend, Martin Luther King weekend, and I'll see you guys on Tuesday.